Guess what time it is? It's time for Chem 1105 with your host, Dr. White, me. Happy September 1st, everybody. Boy, does this year gone quick. It's already September. Before you know it, it'll be December and we'll be done. Oh, that's a sad thought. But anyways, couple important things. Don't forget, tonight from 5 to 6:15, I have my office hours. If you have any questions, come on by, I'll help. Also, I was just wondering if, how should I phrase this? If the time I have my office hours are not good for you, let me know. I'll see if I can adjust them because I'm here to help. The other thing I found out the last day or two from a couple students is they have gotten invalid access code from the bookstore. Don't ask me. Happened once this last summer too. And what I'd recommend you do, if you have an invalid access code from the bookstore, call them. Don't email them, call them and tell them what the problem is and that they need to not mail, but email you a new access code because you need it to do our labs. And if you have any problem, email me, let me know, and I'll get involved and then I'll call them. But first, you should call them because you bought that from the bookstore, not from me. Well, that'd be a good racket. Hi, you want to buy an access code? No, I can't do that. But anyways, don't forget, if you had a bad access code, call the bookstore if you bought it from them.
I just wanted to say that when I got my access code, I had to log into the 2.0 version first and then convert it to 3.0 to make it work.
Really?
Yeah, so that's how I got mine to work.
All right, would you say that again?
I had to create my account through the 2.0 version and then press convert to 3.0 for my account to work in the 3.0 version.
Yeah, I'm trying to find. Mia, thank you very much for sharing that. I appreciate it. I'll have to talk to the people at Beyond Lab Z about that. I wonder if they know about it. Interesting, I got an email last night about 6 o'clock from people I know at Beyond Lab Z, one person. And guess what? They finally ported it. It's in beta. And if you don't know what beta version means, it means they made it. They've done just a little testing. And there's still some bugs in it. And I found a couple yesterday of the density lab. You want to take a look at it, but I think it'd be safer to go to the desktop version. But Mia, thank you again for sharing that. And those of you who had trouble with the access code, why don't you try Mia's fix and see if it works? And I'll ask you to do a favor. If that does work, please let me know. Which it means, I guess, the bookstore is sending out old access codes. That's not good. All right, let's get to work. Yesterday, we were talking about the atom. I talked to you about Dalton's theory, atomic theory, and he was the first one to really push the concept of an atom, what it is, and how it's used to make up molecules, compounds. Next, I talked to you about the subatomic particles of an atom. Those are the particles that make up an atom. And you should know these. Hint, hint, big hint. And everybody together, you don't have to turn on your mic, but together with Dr. White, the three subatomic particles are the electrons, the protons, and the neutrons. Let's do it again. It's fun. Come on, you can do it with me. Everybody together with feeling. The three subatomic particles are the electrons, the protons, and the neutrons. And you should know electron has a negative charge, electrical charge. Proton has a positive electrical charge, and a neutron has no charge. Now, I talked about yesterday Rutherford's gold foil experiments, which elucidated, that's a fancy word meaning figured out the nucleus, which is the center of the atom, something you should know. And the nucleus contains only protons and neutrons. Again, the nucleus, center of an atom, contains only protons and neutrons. And I talked about the atomic number. The atomic number, by definition, equals number of protons. And because all atoms have a net zero charge, and all atoms of the elements have a net zero charge. Therefore, if you have so many protons, which are plus charge, that also has to equal the number of electrons. Now, what I didn't do, and I better do it right now, is open my periodic table. And hopefully you all see the periodic table. If not, scream at me. No, you don't have to scream. Let me know. All right. Remember, the atomic number of the periodic table is the number for the table I'll give you in the upper right-hand corner. Once in a while, you'll see a periodic table. It's in the upper left-hand corner, but it's always at the top of the box. And hopefully you all know right from left. And if I ask you how many electrons and protons does nitrogen have? Ooh, that's a hard question. Because first of all, what's the chemical symbol for nitrogen? And you have to find it on the periodic table here. And the atomic number 7 tells you how many electrons and protons. 7 protons, 7 electrons. Ooh, let me test you. How many electrons and protons does potassium have? Your turn to have some fun. Time's up. Let's look. Potassium, chemical symbol K. It's an alkali metal, first column, and it has atomic number 19. That means it has 19 protons and 19 electrons. Oh, let's try one more. Oh, let's look at a dangerous compound, and it is, and that's mercury. How many electrons and protons does mercury have? So everybody's eyes are scanning around the periodic table trying to find it. And hopefully by next Tuesday, you'll learn that mercury, the chemical symbol Hg, has atomic number 80. Therefore, it has 80 electrons, 80 protons. Now, why do I say mercury is dangerous? Because it is. It's a cumulative poison. As you get any in your system, it stays there and keeps on building up until it does serious harm or kills you, which is why most of you are not familiar with medical thermometers that came with mercury. When I was a boy, my parents had one in the house. My doctors used it. We even had a little game. I don't know how they could do it, which was a little maze with a drop of mercury, cardboard back, and you went like this to move it through the maze. My cardboard back never ripped, but if they did, and I'm sure they did, you now have some mercury poisoning. Yeah, let's go back to some nicer thoughts. And I'll talk later on about the atomic mass, but that's the number, and switches off, click for this slide. It's the number of protons and neutrons in a nucleus. Now, I think I ended here. Switch is still off, but later on I'll talk about isotopes. And isotopes are elements that have the same number of electrons and protons, but different number of neutrons. How many of you have ever heard of carbon-14 dating that archaeologists use to determine how old something is? What they do is measure the amount of carbon-14. Carbon normally has 12 neutrons, but in carbon-14, there are 14. And it decays to 12. And by how many there are, you can get the age of something. Now, I should have taken this off because in all the years of chemistry, I've never used the nuclear symbol. But if you ever need to look at it, you can know you heard it briefly from Dr. White. Switch is totally off on this slide. And same thing with the atomic mass. I'll briefly mention it. Scientists, chemists have been able to find out the abundance, how much for every element each isotope is present on our planet. And to get the actual atomic mass, it's a weight average mass. If you have 80% of one and 20% of another isotope, you take 80% of this weight, 20% of this, average them together, and that's where you get the atomic mass. So I have never in my career ever had to do that. So I'm not going to ask you to learn how to do that, but at least you know where it came from. And the atomic mass is the number underneath the symbol of the element in the periodic table. If you look at carbon as 12.011, and that's because there's some carbon, most of it is carbon 12, but there's a small amount of carbon 13 and 14. Same thing with oxygen, 15.999, and that's the atomic mass, which I will call in the future the weight, because we're not leaving this planet. At least all of you said you weren't, and I'm not. And that's the weight average of the different isotopes of oxygen. The most prevalent is oxygen 16. Like I said, well, no, I haven't said. In case you haven't figured out, I live in the real world and I've worked in the real world of chemistry. So stuff just because it's in the book, but you're never going to encounter it because I never have used it. I'm not going to teach you. I'll mention it, but I'm not going to ask you to know this for a test because it makes no sense. And that way I'm a realist. And let's just do a little more practice of the periodic table. Let's locate an element, determine the atomic number, and determine the number of electrons and protons. Let's hold off on the atomic mass. All right, everybody, find out what's the atomic number, or another way of saying it is, how many protons and neutrons does iron have? Time's up. Iron, Fe, right here, has atomic number 26. So it has 26 protons, 26 electrons. Now, one of my favorites, chlorine. How many protons and neutrons, not neutrons, electrons, does chlorine have? And the answer is, remember, chlorine is a halogen in the second to last column, Cl, atomic number 17. Therefore, it has 17 electrons, 17 protons. Let's do one more. Ooh, this is an important one for our daily life. Calcium. How many electrons and protons does the element calcium have? Remember, you need calcium for strong bones. All right, calcium, chemical symbol, Ca. And the atomic number is 20, and therefore it has 20 electrons, 20 protons. Ooh, I just remembered I forgot to say something. Time for a public service announcement from your host, me, Dr. White. On Friday, I will go through the practice problem set for Appendix A2 and A4. On Friday, I'll go through the practice problems for Appendix A2, A4. I highly, highly recommend you do them before I go through them. That way, if you have any questions, you can ask questions. Because don't forget, in my class, in my world, in my universe, there's no such thing as a dumb question. All right, let's move on. Now, Rutherford found out that in an atom, which is made up of electrons, protons, and neutrons, in the center, very dense center, are the protons and neutrons. And the question is, where are the electrons? They've got to be there. Where are they? Well, they're around the nucleus. And in order to talk about that, I have to talk about electromagnetic radiation and aspects of it, because that will help you understand where are the electrons. And in my personal opinion, the electrons are the most important part of an atom, because that's what holds atoms together to make molecules like my skin or your skin. I'd say that's pretty important. So when we talk about electronic structure, meaning where are the electrons, we have to talk about electromagnetic radiation. By the way, click switches off for this slide, but it's important background information we need to talk about. Now, electromagnetic radiation is energy that travels as waves through space. And this radiation, because it's like waves, I'd like the special effects. Pretty poor. But anyways, like when you go to the ocean and you see like the Atlantic or Pacific Ocean, not so much Lake Michigan, but sometimes in bad storms they do, the waves coming in, and they have both wavelength, how far apart they are, and how fast they come in, frequency. And to show this, we have what's called the electromagnetic spectrum. It's an arrangement of all, again, switches off for this slide, an arrangement of all various forms of electromagnetic energy in order of decreasing energy. Let's go out to the internet. Does everybody see the electromagnetic spectrum on your screen? Thumbs up, people. Thank you. And if you look at this, you'll see here are the waves. And at the low end, we have radio waves, then TV. And that looks like one of my old routers on there, and your cell phone. Then as we go from left to right, you have higher energy things. Right around in the middle here, right here between infrared and ultraviolet, we have visible light. And notice their different colors have different wavelengths, or you can also say frequencies. And how many of you remember from high school? I still do Roy G. Biv for the rainbow. Red, green, never mind. Anyways, and as you get higher up to the right, the wavelength decreases and you get higher energy, X-rays, gamma rays. So these different, like in the light, corresponds to different energy levels. And that's the important thing about electromagnetic spectrum, that for light, the different colors correspond to different energy levels. Well, chemists long ago found out that certain elements, when you heat them, give off light. How many of you have ever seen fireworks? Back when I was your age, and before they paired it with the music, which I don't like, I used to go with a bunch of friends of mine down to Chicago to watch the 4th of July fireworks show, which I love. And my friends and I, if you haven't noticed, I'm not a small person, and my friends weren't, so we got good spots by the lake shore to see it. And when they explode, that's forming different colors of light. And we call that atomic spectrum. Let's see something real quick. I don't know if you can see it well, but let me. Does everybody see hydrogen, helium on your screen right now? Maybe not. Yes, you should. All right. If you heat up hydrogen, you see these two lines are mainly, if you heat up oxygen, see all the different lines there? That corresponds to different energy levels of what? Of electrons in the molecule. And that's the atomic spectrum. And when light is emitted from elements, it's passed through a prism. That's a glass one. Oh, my two are downstairs. By the way, I have a collection of prisms. Yes, I'm a scientist. I like that stuff. And it separates them into different lines or colors. And these different lines are energy levels. And there are the associational lines in the atomic spectra with changes in energy levels of electrons. And these energy levels, switches off on this slide, are assigned principal quantum numbers called n, and these energy levels are called shells. So where are the electrons? They're around the nucleus. They're in different shells. Time for me to be subtle. All right, when we talk about where are the electrons, you should know, hint, first of all, the electrons are in the electron shells, and the shells are a region of space about the nucleus. Remember, the nucleus is the center of the atom that contains the electron shells, contain electrons that have approximately the same energy and spend their time approximately the same distance from the nucleus. So this is the shells. Now, each shell has what we call electric subshells, or I'll just say subshell because I'm a lazy organic chemist. And this is a region of space within an electron shell that contains the same electrons that have the same energy and are also the same distance from the nucleus. So we have the electron shell, which contains electrons of approximately the same energy. And in the electron shell, we have electron subshells. And in the subshell, the electrons in the subshell have the same energy. Now, common misconception is I have my nucleus, and around here, I have my electrons, and they're like the planets around the sun. No, they're approximately there. They don't rotate like the planets. It's much more complex, which we won't get into in this semester, but trust me, it's much more complex than planets going around the sun. Now, when we talk about the electron shells, now, in the past, I used to make students memorize this, but I will be giving you this in a table, important information, test number 1. But you should understand, the shells have very complex names. The first shell is called 1, the second shell 2, the third shell 3, and the fourth shell 4. So remember, a shell is where you have electrons with approximately the same energy and approximately the same distance from the nucleus. Now it's going to get real complex. Shell 1 has 1 subshell. Shell 2 has 2 subshells. Shell 3, guess what? It has 3 subshells, and shell 4 has 4. So the shells, very, very complex names, 1, 2, 3, and 4. Now, something you will have to remember is when we have the shells, this is very important to remember. When you go down, going to higher shell numbers, shell 1 is the lowest energy shell of all shells in an atom. And as you go down, 2 is greater than 1, 3 is greater than 2, and on this chart, 4 is the highest energy. And that's what we have. Now, something I should show you right now. Hold on while I open up this file. All right, everybody see on your screen important information, test number 1. Thumbs up, people, do you see it? Uh-oh, hold on. All right, you should see test number. Thank you, Elena. All right, this is stuff you do not have to memorize for test number 1. In test number 1, you'll have a number of pages, and the last page will be this page. And notice I give you the table electron shells. And I'll also talk about it in a second. I'll give you the subshell table. In the past, students had to memorize this. You can say, thank you, Dr. White, you're welcome. And I decided I should test your knowledge of chemistry, not how good your memory is. And that's why I provide this. Let's go back. Now, again, the electron shells have the name 1, 2, 3, and 4. And shell 1 has 1 subshell. Shell 2 has 2 subshells. Shell 3 has 3, and 4 has 4. Like I showed you, you'll be given this table. But you have to know shell 1 is the lowest energy, and when you go down the table, shell 4 is the highest. And going down is increasing energy. Now, subshells have letter designations, and they are S, P, D, and F. I hope you all enjoy when I'm being subtle. Hint, know this. And S, P, and D, and F. And S is the lowest energy subshell. And when you go from left to right, you go from lowest energy subshell to highest energy. Does everybody know this symbol means less than? Now you do. And S is the lowest. Energy, and F is the highest. It goes this way, just like I have above. Now, this won't be on test, but a couple of years ago, one of my students asked for, what does S, P, and D, F stand for? And I didn't know, I'd forgotten. And I went back and looked it up, and this will never be on a test. And this comes from the atomic spectra when chemists were looking at those lines. I don't know how they came up with these names, but S stands for sharp, P is principal, D is diffuse, and F is fundamental. How they came up with that, don't know. But I know it comes from looking at atomic spectra. Now, when we talk about the subshells, it's important to know that subshell S can only have maximum number, and this should be really max number of electrons, 2. P, you can only put 6 into. D, you can put 10 into, and F, you can put 14 into. Again, subshell S, you can put up to 2 electrons in. P, you can put up to 6 electrons, and D, 10, and F, 14. Now, as I mentioned earlier, I've cut back on memorization. And if you look on important information, test number 1, I give you that table. But you have to know S is the lowest energy, F is the highest. And as you go down the table, you go from lowest energy to highest energy. But you don't have to memorize how many electrons, but let me write here. So S is the lowest energy subshell, then P, then D, and F is the highest. S, you can put maximum of 2 electrons, P 6, D 10, F 14. And this is how Mother Nature, or whoever created it. It's something chemists were able to determine by doing experiments. It wasn't just somebody said, oh, let's make S2, P6. No, in real life, that's what it is. Just like, how many fingers do you have? 5, not 8, because you can count them. 1, 2, 3, 4, 5. Same thing here. Now, I'm going to turn the switch off for the next couple of slides. Click. Now, besides shells and subshells, we have something called orbitals. That's a region in an atom where there is the highest probability of finding electron. What that means is, if Dr. White was all powerful and I could stop all motion and time in our world, boy, I'd really be powerful. Stop, but I can't. But if I could, orbital, electrons are moving around the nucleus. And if you stopped everything, orbital is the area where you'd probably find that electron. It's a probability because it's always moving around, but if you could stop it, that's where you'd find it. And orbitals have shapes, switches off. S is circular, spherical. P orbital looks like an hourglass, and anywhere between these two lines, you can find that. Now, I won't teach in this class, but P orbitals and S orbitals are really important, the other ones too, but P orbital helps make double bonds, which I'll teach you about later. And how many of you have heard of unsaturated fats? And it's because of a p orbital, we have unsaturated fats, which are healthier for you than saturated fats. I'll teach you that later in the semester. Now, switches off. Oh, wait, I take it back. Switches on. Yeah, make it some, I'll clarify this later. But anyways, electron subshells are filled in order of increasing energy. Now, I'll mention this later, a lot of times. You always fill the lowest shells, energy shells, and subshells in a shell first with electrons. And this one I won't really cover in this class. Electrons occupy orbitals of a subshell such that each subshell acquires 1 electron before it acquires second. That's called the Busse rule. And no more than 2 electrons can exist in an orbital, and orbitals exist in subshells, which exist in shells. For those of you who are confused, I'm sorry. Let's get back on track. Now, question is, where are the electrons? Aren't you glad I can be really subtle? And where are the electrons? We show that one way is by electron configuration. What is electron configuration? It's a statement of how many electrons an atom has in each of its subshells. Now, hint, you only use numbers and letters. I could even expand on this: numbers, letters, and superscript numbers. How do you do electron configuration? Well, let's take a look. And say sometime in the future, you see on a screen or a piece of paper you print out that I sent you, 3 points each, draw the electron configuration for a lithium. Well, what do you do? Well, the first thing you have to do is find out how many electrons does lithium have. Well, how do I do that? Well, I go over to my friendly neighborhood periodic table. I stole that from Spider-Man. But anyways, and you see lithium. How many electrons does lithium have? Lithium, chemical symbol Li, atomic number 3. You now know it has 3 electrons. So we have 3 electrons to deal with. That's shorthand for electrons. Now, you always fill electrons in the lowest shell and subshells first. And the lowest shell is 1. And its subshell is S. And a subshell is designated by a number and a letter. So the first subshell in lithium is 1s. And if you go back and look at the table here, the lowest subshell, the first one, lowest energy you fill always first is 1. What's the lowest subshell in 1? 1s. Now, how many subshells does 1 have? 1. So it's only 1s. What's the maximum number of electrons I can put in 1s? Any s orbital is 2. So how do I show that? By doing that. Now that tells me I have 2 electrons in subshell 1s. Remember, a subshell is a number and a letter. Now, how many subshells does 1 have? And the answer is 1. And how many electrons can we put maximum in 1s? Well, in any s orbital, subshell, not orbital, subshell, once in a while I make that mistake and correct myself immediately, which I just did, you can put 2 electrons. Well, we've done that. And 1 has only 1 subshell, S, and we filled it. So we can't put any more electrons in shell 1. So now we have to go to shell 2. What's the first subshell in 2? 2s. How many electrons can I put in there? I can put in 2. But how many do I have left to go? 3 minus 2 equals 1. So I'll put that 1 electron in there. And this is the electron configuration for lithium. 1s2, 2s1. And that's how you do it. And think of this as sort of an accounting chemists use to determine where are the electrons. And certain branches of chemistry, knowing the electron configuration is quite useful to determine aspects of lithium. Let's see how much time I have left. Oh, we got enough time. Let's do another one. My favorite, carbon. And again, the question is, draw the electron configuration for carbon, 3 points each. I want those 3 points, so what do I have to do? Well, first of all, you have to find out how many electrons does carbon have. And you go to your friendly neighborhood periodic table, carbon, chemical symbol C. The atomic number tells you how many electrons, 6. So carbon has chemical symbol C, 6 electrons. And now I know I have 6 electrons to deal with. Well, what's the first subshell or shell? 1. What's the first subshell? There's only one, and that's S. How many electrons can I put in S? Well, in case you forgot, let's take a look. Shell S, you can put up to 2 electrons. So I'm going to do that. Well, I have 4 more to go, so I'm not done yet, because 6 minus 2 is 4. And I've got to show all 6. Well, if we look at shell 1, how many subshells does it have? 1. And now I filled it up because 1s can only have 2 electrons. So now I go to shell 2. The first subshell in 2 is 2s. Well, let's go there. Remember, subshell is a number and a letter. How many electrons can I put in any S subshell? Well, you don't have to memorize it. The number is 2, because you'll be given this an important information test number 1. So I'm going to put 2 in there. Well, I've got 4, but 6 minus 4, I've got 2 more to go. Well, how many subshells does shell or 2 have? Well, let's go look at our table, which you'll have. Oh, look, shell 2 has 2 subshells. And the first one is S, and you go lowest to highest down to shell. The second one, or 2s, the second one would be 2p. And if you look here, notice I can do max number of electrons, 6. I don't need 6, but I could if I had to. And so the second subshell in 2 is 2p. I have 2 more electrons to go. I could put 6, but I only need 2. So for carbon, the electron configuration is 1s2, 2s2, 2p2. Oh no, if I look at the clock, our time's almost gone. Boy, time flies when you're having fun with protons, neutrons, and electrons, and Dr. White. Don't forget, you should have handed in the lab yesterday, the safety lab. If you didn't, I'm going to give you a grace period till tomorrow morning. I won't take off any points. Get it in if you haven't. Important thing about labs, we are face to face. I would hand back the lab the next lab period. Because we're not going to do that, I'll post the scores in Blackboard. Usually I do it on the weekend, but check. I've done half of them already. I graded them yesterday. And unfortunately for labs, I can't give back a paper and say, here's what you got wrong. But remember, in my class, there's no such thing as a dumb question. You can always ask me, why did you take off points on anything else? I figured out a way to test how for you to see for each question what you got wrong. But with that, I went a whole 60 seconds over. I'm sorry. With that, I'm going to say, don't forget, Friday, I will go through the problem set for Appendix A2, A4. You do that. And with that, I'll say, gehen gesund, goodbye, be healthy. That's what gehen gesund means, or go in health. And don't forget, wear your mask and get your vaccination if you haven't. Bye.